Hierarchical agglomerative clustering provides a range of solutions, but it leaves you with an important question. How many clusters should you create? One way to decide is by creating a dendogram and analyzing it. But what exactly is a dendogram? Let's revisit our earlier example with 5 objects. Initially, each object forms its own cluster, resulting in a 5-cluster solution. This is represented as P1 in the graph, where each object stands alone in its own cluster. Hierarchical clustering then proceeds by merging the 2 closest clusters to create a 4-cluster solution. In this case, the clusters containing object 1 and object 2 are the closest, so they are combined. The dendogram on the left visually represents this merge. P2 now contains 4 clusters, one with object 1 and 2 together and 3 separate clusters for objects 3, 4 and 5. You'll notice a fork connecting objects 1 and 2 in the dendogram. Every fork represents a merger of 2 clusters, and the height of the fork indicates the distance between them. For example, the fork joining objects 1 and 2 reaches a height of 2, meaning they were separated by a distance of 2 before merging. Next, we move to a 3-cluster solution. This is achieved by merging the clusters containing objects 4 and 5. The corresponding fork in the dendogram reflects this merger, and since this fork is slightly higher than the previous one, it indicates a larger separation with a distance of 3 in this case. We then merge the cluster containing object 3 with the newly formed cluster of objects 4 and 5. The dendogram shows this connection through another fork, where the distance between the clusters is 4. Finally, we reach the last step, merging the remaining 2 clusters into one. The corresponding fork connects all the objects, reaching a height of 5 in the dendogram. Now let's look at a real-world example using a dataset of cars described by several variables. The challenge is to group similar cars into clusters. In the dendogram, you'll notice a prominent fork at the top with 2 long legs, indicating that the 2 clusters on either side of the fork are very different from each other. One way to decide on the number of clusters is by cutting the dendogram at this top fork, resulting in a 2-cluster solution. If you examine the dendogram further, you might spot another fork below the top one, with relatively long legs. Cutting here would create a 3-cluster solution. As you move lower down, the forks become shorter, suggesting that those clusters are quite similar and don't need further separation. Ultimately, determining the number of clusters is not an exact science. The dendogram offers a visual guide, but it also requires intuition and judgment. You might test both 2 and 3 cluster solutions, analyze the results, and decide which one makes the most sense for your specific problem. This is how you create and interpret a dendogram to determine the optimal number of clusters for your data.